All right, so let's get started again. So we're extremely happy to have Cemil here today to tell us about a way of going between perfect graphs and sums of squares. Take it away, Cemil.
Thank you. Can you see my screen?
Yes, we can.
Okay. All right. So thank you all for coming. Thank you for inviting me. I'm also sorry that I was not able to come in person. I really wanted to, but it was simply infeasible this time. Though I'm really hoping that I'll have another chance to visit UMass some other time. Okay. This is a joint work with Amir Ali Ahmadi from Princeton, and this result is about the relationship between two objects, one from graph theory, namely perfect graphs, and the other is from convex algebraic geometry, which is sum of squares polynomials. So what I will do today is, first I will tell you a little bit about sum of squares polynomials, a much shorter version what I presented in the pre-seminar. Then I'll tell you a little bit about perfect graphs, just the definition. And after that, we will see how we can establish a link between these two notions. Okay, so let me start by introducing sum of squares polynomials and perfect graphs. I'm having an issue. I think, just a second. Okay, you can still see my screen, right? Yeah. Okay, perfect. So, okay, so I'm sure many of you are familiar with these concepts, but just to have some formal definitions, let me start with the basics. So what is a non-negative polynomial? A multivariate polynomial P in n variables, x1 to xn, is non-negative if P of x is greater than or equal to 0 for every x in Rn. So as you might know, and as we were discussing in the pre-seminar, there are many applications in applied mathematics that involve certifying non-negativity of polynomials. And I have shown some examples where checking non-negativity of polynomials appear. However, simply deciding non-negativity of a given polynomial is NP hard in general. Still, there are some ways of certifying non-negativity. And one way to do that is to try to write the polynomial as a sum of squares of other polynomials. For instance, here, this polynomial and this polynomial, they are the same polynomial. And it would be really nice to see that it can be written as follows, because this would tell us immediately that it is non-negative, because it is sum of squares. So what is sum of squares? We say that P, a polynomial P, is sum of squares, or SOS in short, if it can be written as sum of squares of other polynomials. And obviously, every SOS polynomial is non-negative. And I finished in the pre-seminar with the following two questions. So these are very natural questions that come to someone's mind as soon as we see the definition of SOS polynomials. So the first one is, okay, it's hard to check non-negativity, but is it easy to check if a polynomial is SOS? And second, okay, every SOS polynomial is non-negative, but is every non-negative polynomial is SOS? And the answer to the first one is yes. We can easily check whether a given polynomial is SOS or not by solving a single semi-definite program, as is well known. And the second question has also been studied for a long time. And as most of you know, the answer is negative. And that was shown by Hilbert in 1888. So now let me tell you a little bit about Hilbert's theorem. So in 1888, so the issue that I'm having is that I cannot see my screen. So just, I'll try to share it again. I'm really sorry for this. Okay. Okay. In 1888, Hilbert showed that not every non-negative polynomial is SOS. More precisely, he showed that a non-negative polynomial of degree d in n variables is SOS if and only if n is 1, or d is 2, or nd is 2, 4. In every other case, there are some non-negative polynomials that are not SOS. And in particular, the minimal cases for which this happens are 2, 6 and 3, 4. So degree 6 in 2 variables and degree 4 in 3 variables. However, Hilbert's proof was not constructive in the sense that he didn't provide an explicit example of a non-negative but not SOS polynomial. And if you think about it, it's not that immediate to come up with such examples. For that, we had to wait 80 years when Motzkin in 1967 gave this example for the case 2, 6, 2 variables and degree 6. And then a few years later, Robinson gave this example for the case 3, 4. Okay, so these are the first non-negative but not SOS polynomials that appeared in the literature. But then in 2003, Blackerman showed that, in fact, if you fix the degree, and if you let the number of variables go to infinity, there are many more non-negative polynomials than SOS polynomials. But again, this was done through a non-constructive argument, through a volume argument. So this again didn't give several examples of non-negative but not SOS polynomials, although several examples appeared in the literature since then. To this day, it still seems to be a non-trivial task to construct non-negative polynomials that are not SOS, especially in low degrees and dimensions. Okay, so this is a very short story of SOS polynomials, and next I will introduce perfect graphs. Okay, so here are two important parameters of a graph, the clique number and the chromatic number. A clique in a graph is a set of pairwise adjacent vertices, and the clique number is the size of a largest clique in a graph. A coloring in a graph is a labeling of the vertices with colors such that adjacent vertices receive different colors. And the chromatic number is the smallest number of colors that are needed to color a graph with the condition that I just described. And we have the following inequality between these two parameters. The chromatic number is always greater than or equal to the clique number, simply because if you have a clique in a graph and if you want to color this graph, then of course you have to give a different color to each vertex of that clique because they're all adjacent to each other. So the clique number is greater than or equal to the chromatic number. Sorry, the chromatic number is greater than or equal to the clique number. And for some graphs, such as this one, these two parameters are the same. And for some graphs, such as this one, they are not the same. So what is a perfect graph? A graph is called perfect if omega and chi are the same for every induced subgraph of the graph. So induced subgraph of a graph is simply a subgraph which is obtained by deleting vertices. So in order to be a perfect graph, this condition should hold for every induced subgraph, including the graph itself. For example, this graph is not perfect simply because the condition already fails for the graph, and this graph is perfect not only because these two numbers are the same for the graph, but also they will be the same for every induced subgraph. And perfect graphs are important objects in graph theory and optimization. They link various mathematical disciplines. And one important result about perfect graphs is this one that I introduced in the pre-seminar. This is called the Theorem perfect graph theorem. And it gives a structural characterization of perfect graphs. It says that a graph is perfect if and only if it contains no odd holes and no odd antiholes. So odd holes are simply odd cycles of length at least 5, which we denote by C5, C7, and odd antiholes are their complements. And if you think about it, you will realize that indeed perfect graphs cannot contain odd holes and odd antiholes because the clique number and the chromatic number are different for these graphs. But the converse direction is the actual theorem, which is long and relies on structural graph theory, and it's highly non-trivial. Okay, good. So now that I have introduced both sum of squares polynomials and perfect graphs, let me now introduce a new notion that brings together these two notions, which we call SOS perfect graphs. So first, we define a polynomial. For a graph G on n vertices and with clique number omega, we define the following polynomial, Pgx. So it goes as follows: minus 2 omega times sum of these monomials, xi square, xj square. So for every edge in the graph, we have one of these monomials, plus omega minus 1 times xi, sum of xi square square. So for every vertex I in the graph, we have a variable xi in the polynomial. The first thing to observe about this polynomial is that it is degree 4. Indeed, it's homogeneous, so each monomial has degree 4. And the second thing to observe, it's not immediate to see, but I will show you why. It's also true that this polynomial is always non-negative, meaning that for every graph G, this polynomial is a non-negative polynomial. And whenever you have a non-negative polynomial, you should ask, when is it SOS? And so we define the following notion. A graph G is SOS perfect if this polynomial, if PHX is SOS for every induced subgraph H of G. Okay, yes. I think there's a question.
Yeah, Cemil, I was wondering, can you give a little bit of intuition for how you came up with this polynomial that will play an important part?
Yes. So this will appear in the proof, but if you want a short answer, the short answer is it comes from the Motzkin-Strauss theorem, but it's going to appear in the proof clearly how it comes.
All right, thank you.
Okay, so this is the definition of being SOS perfect. Let me maybe show you a quick example. So here is a graph G, and here is our polynomial PGX. If you write this polynomial for this graph G, you open this, and we can easily show that it is actually SOS. Here is a sum of squares decomposition. Well, then you have to do this for every induced subgraph. And if they are all SOS, such a graph is called SOS perfect. Okay, good. Now that the definition of being SOS perfect graph is hopefully more clear, let me introduce the theorem that I wanted to share today. So a graph is perfect if and only if it is SOS perfect. So this gives an algebraic characterization of perfect graphs. Essentially, it says that a graph is perfect if and only if certain non-negative polynomials associated with the graph are SOS. Any questions about the definition or about some other parts before I move to the proof?
Could I see the example from the previous slide?
Sure. So here we have the graph G, and it has 4 vertices, and therefore it has 15 induced subgraphs, 2 to the 4 minus 1 induced subgraphs. And when we write this polynomial for each of these induced subgraphs, if they are all SOS, then we conclude that this graph is SOS perfect. Does that make sense?
In the definition, you have to be a sum of squares of the subgraphs.
So each induced subgraph
Each induced subgraph.
needs to be sum of squares.
Each induced subgraph. Okay, thank you.
Yes, exactly. Should I continue? Is that it? Yeah. Okay. Yeah. All right. So as you will see soon, the proof builds on several interesting results from graph theory and optimization. And in the rest of the talk, what I will do is I will first give some ideas of the proof, and then I will show you one important implication of this theorem, which might be of interest to the SOS community in particular. Okay. All right. So I'm really sorry, but I will try this again. I'll stop sharing and then share again. Okay. All right, good. So we want to show that perfect graphs and SOS perfect graphs are the same. Well, it turns out that the key parameter that plays an important role in the proof is the Shriver number of a graph. I mean, I called it Shriver number, but it was actually introduced by Shriver and by another group independently. But for the rest of the talk, in the rest of the talk, I will just call it the Shriver number. So what is this? This is a semi-definite program which takes a graph as an input, and based on the adjacencies in the graph, it outputs a real number. So here, the decision variable is an n by n symmetric matrix. And here J is the matrix of all ones. So the objective function simply says that maximize sum of the entries of X. And then we have some affine constraints on the entries of X. And these two last constraints, they say that X is positive semi-definite, and this says that X is entry-wise non-negative. Okay, so this is a semi-definite program, but a very useful one, because Loas and Shriver showed that this number applied to the complement, and whenever I say Shriver number, I mean applied to the complement, this number is sandwiched between the clique number and the chromatic number. So what I'm going to say now has nothing to do with the proof, but it's worth mentioning. I think it's a good note. This is amazing for perfect graphs, right? Because for perfect graphs, the clique number and the chromatic number are the same by definition, and so all these 3 numbers are the same, which means that we can find the clique number of a perfect graph by simply solving this semi-definite program, which can be done in polynomial time. In general, finding the clique number is NP hard, but for perfect graphs, we can find the clique number and by solving this semi-definite program. And remarkably, this is the only known way to find the clique number of a perfect graph. And it's a huge open problem to come up with a combinatorial algorithm to find the clique number of a perfect graph without using this semi-definite program. Okay, so this was just a quick note. And so if we go back to our proof, what we will do is we will show these two lemmas, lemma 1 and lemma 2. Lemma 1 is more on the optimization side. It says that PGX is SOS if and only if the clique number and the Shriver number are the same. So it essentially characterizes exactly when this polynomial is SOS. And the second lemma is more on the graph theory side. It says that a graph is perfect if and only if the clique number and the Shriver number are the same for every induced subgraph. So I will tell you, of course, about these lemmas, but if you believe these two lemmas for a moment, then the proof of the theorem follows immediately because, well, G is perfect if and only if by lemma 2, the clique number and the Shriver number are the same for every induced subgraph, which holds if and only if by lemma 1, PHX is SOS for every induced subgraph, H of G, which is the definition of being SOS perfect. Right, so if you believe these two lemmas for now, then the proof of the theorem follows immediately. Now I'll tell you about lemma 1 and lemma 2. Let's start with lemma 1. The proof of lemma 1 builds on some previous results. So here we want to show that PGX is SOS if and only if the clique number and the Shriver number are the same. Let's show something more general. So here we have our polynomial PGX. Let's obtain a more general polynomial by simply replacing this omega by a scalar k. So this is called PGKX, which was obtained from PGX by simply replacing omega by a scalar k. And what we are going to show is this lemma 0, which says that this PGKX is non-negative if and only if k is at least omega, and it is SOS if and only if k is at least the Shriver number. So it's also useful to look at this lemma from the complexity point of view, because if you remember, I told you checking non-negativity is hard, but checking if a polynomial is SOS can be done by solving a single semi-definite program. Similarly here, finding the clique number of a graph is NP hard, but computing this Shriver number is a semi-definite program. Okay, so if you believe this lemma 0 for a moment, then lemma 1 follows immediately, because what is PGX? PGX is simply PGKX, k replaced with omega, right? So if you replace k with omega in part A, you immediately get that PGX is non-negative for any graph G, which I told you before. This polynomial is non-negative for every graph G. And if you replace k with omega in part B, you get that PGX is SOS if and only if omega is at least the Shriver number. But we know that omega is at most the Shriver number for any graph, and therefore we get exactly lemma 1, which we wanted. But now I need to tell you about lemma 0. Okay, so now let's do that. For lemma 0, so I just put it here. So for lemma 0, let me first introduce this set of copositive matrices. Just to remind you, this is the set of matrices M such that X transpose X, X transpose MX is non-negative for every X, at least omega, for every non-negative X. And we denote this set of matrices by Cn. So here is the Motzkin-Sutras theorem. If you have seen this theorem before, you probably haven't seen it in this form, but with some efforts, it can be put in this form. So this is a very beautiful theorem. I mean, it gives a copositive programming formulation of the clique number. It says that the clique number is the minimum k such that this matrix here is copositive. Here, J is the matrix of all ones, and A is the matrix is the adjacency matrix of the graph. Okay, and so the clique number can be found by minimizing k such that this matrix is copositive. Here's a quick remark. It's a very simple observation. So a matrix being copositive can be turned into a polynomial being non-negative. A matrix M is copositive if and only if this polynomial, which was obtained by the entries of M, is non-negative. This is, again, a very simple observation that you can check. And so we can describe the set of copositive matrices as follows. Matrices M for which this polynomial is non-negative. As I said before, whenever you have a non-negative polynomial, you should consider replacing it with being SOS. And so let's replace this condition with being SOS and obtain this set Kn. So this is the set of matrices M for which this polynomial is SOS. And of course, Kn is a subset of Cn, because if a polynomial is SOS, then it is non-negative. So if you're in Kn, then you're also in Cn. Then the question is, if you go back to Motzkin-Strauss theorem and replace this Cn with Kn, a smaller subset of Cn, what do you get as an optimal value? And that was shown by de Klerk and Pasechnik. You get exactly the Shriver number. So again, if you have seen a similar result before, probably you haven't seen it in this form, but with some efforts, we can put these optimization problems into this form. Cn and Kn formulations of the clique number and the Shriver number. Well, then it's easy to finish, because this matrix here is copositive. It's the same thing as saying that this polynomial here is non-negative. So if you write this polynomial for this matrix that you see here, you get exactly PGKX. So PGKX comes from turning this matrix into a polynomial using this observation. And so we obtain these two formulations of the clique number and the Shriver number. So the clique number is the minimum K such that PGKX is non-negative, and Shriver number is the minimum K such that PGKX is SOS. These formulations, they prove one direction of A and B of lemma 0, right? They prove that, let's say this first one, it proves that if PGKX is non-negative, then K is at least omega. But the other direction is not that difficult. It's just a few lines, so I'll skip it, and I'll just call it a success. I'll say that we proved lemma 0 and we believe lemma 1. Okay, any questions about this part before I talk about lemma 2? I think there's a question, but I don't hear it.
Yeah, so sorry, I have. So you mentioned that computing the clique number of a perfect graph. So that is a way to do that using this Motzkin-Strauss result, or but is that still a optimization problem?
This is true for any graph, right? And this is a difficult problem because checking if a matrix is copositive is already it's difficult, and finding the clique number is difficult. But in case of the perfect graphs, where did I show it? I think it was here. Yeah, so here, in case of the perfect graph, since this number, which can be computed by solving a semi-definite program, lies between the clique number and the chromatic number, again, for any graph, but for perfect graphs, they are all the same, and therefore we can solve the semi-definite program, and it will give us an integer, which will be the clique number. So this is how we find the clique number of a perfect graph. But the copositive programming formulation is true for any graph. Does that answer the question? Maybe I didn't understand it. Okay, good. Good. All right. So lemma 2 is a little bit more interesting, in my opinion. It says that a graph is perfect if and only if the clique number and the Shriver number are the same for every induced subgraph. So what it says actually, so you remember the definition of being perfect. It is the clique number and the chromatic number are the same for every induced subgraph. But this lemma says that you don't need to go all the way to the chromatic number. If you just check that the clique number and the Shriver number are the same for every induced subgraph, this is also enough for perfectness. Okay. So one direction of this theorem is immediate, because if a graph is perfect, then since the clique number and the chromatic number are the same for every induced subgraph, by sandwich theorem, the clique number and the Shriver number should be the same for every induced subgraph. So that direction is immediate. How about the other direction? Well, what do we want to prove? We want to show that if G is not perfect, then there is a gap between the clique number and the Shriver number for some induced subgraph. That's what we are going to show. So it's enough to prove the following then. If G is a minimal imperfect graph, then there is a gap. So a minimal imperfect graph, by the way, is a graph which is not perfect, but every proper induced subgraph is perfect. So why is this enough? Because let's try to prove lemma 2, that direction of lemma 2, believing this fact. Well, if G is not perfect, then it contains a minimal imperfect graph in it. Let's call it H star. And since we believe this fact, there is a gap for that induced subgraph between the clique number and the Shriver number. which is what we wanted, right? We wanted to show that there's a gap between the clique number and the Shriver number for some induced subgraph. Okay, so how are we going to prove this fact? Well, here's the idea. We have this semi-definite program, which whose optimal value is the Shriver number. So what we can do is we can provide a feasible solution to this semi-definite program with objective value strictly greater than omega. This is a maximization problem. So if you have a feasible solution with objective value strictly greater than omega, then of course the optimal value, which is the Shriver number, should be strictly greater than omega. So here's what we're going to do then. We are going to provide a feasible solution with strictly greater than omega, with an objective value strictly greater than omega. And of course, to do that, we need to use some properties of minimal imperfect graphs, which is our assumption. So here are the three properties that we are going to use. If G is a minimal imperfect graph, then G has exactly n maximum cliques, n being the number of vertices. Every vertex of G is in exactly omega maximum cliques, omega being the clique number. And finally, the maximum clique matrix is non-singular. So what is this maximum clique matrix? It's simply a matrix constructed from the maximum cliques of the graph. So here is an example. The columns represent the vertices, the rows represent the maximum cliques, and you simply put a 1 if that vertex is in that maximum clique and 0 otherwise. This is called the maximum clique matrix of a graph. And in our case, since G has exactly n maximum cliques, this matrix will be n by n. We will have n vertices and n maximum cliques, so this is going to be n by n. Without going into more details, let me just tell you what the feasible solution is. So we provide this feasible solution. We provide this solution. Here, lambda 1 is the smallest eigenvalue of the matrix C transpose C, C being the max clique matrix. And it takes a minute or two to check that this matrix is actually feasible for this semi-definite program. And it gives an objective value, which is exactly this ratio that you see here, which is strictly greater than omega. And so this proves lemma 2. Okay. Okay. So now that we have seen the proof, let me now tell you a nice implication of the results we obtained. If you remember, at the beginning, I mentioned that it's not that easy to come up with non-negative but not SOS polynomials, especially in low degrees and dimensions. Here, I'll show you how we can systematically construct non-negative polynomials. Sorry, is there a question? No, okay. Because whenever you do that, okay, good. So now I'll show you how we can systematically construct non-negative polynomials that are not SOS using some results from graph theory. But let me also say a few words about why this is an important task. So essentially, as I mentioned at the beginning, several important problems in computational mathematics can be formulated as optimization problems over non-negative polynomials. But since these problems are intractable to solve, what is commonly done in practice right now is to replace those non-negativity constraints with sum of squares constraints, which can be efficiently handled. So in this sense, understanding the gap between non-negative and SOS polynomials is very important. In particular, constructing or understanding non-negative polynomials that are not SOS is very useful. So here I'll show you 3 families of graphs that directly lead to non-negative but not SOS polynomials. There are many more graph families, but I have chosen the easy ones to present. And then I will present 3 operations, graph-theoretic operations, that would allow us to generate many more such polynomials, starting from the ones that are not SOS. Okay, so let me start. So the first family is odd holes and odd anti-holes. But let me first quickly remind you, so this was lemma 1, which says that PGX is SOS if and only if the clique number and the Shriver are the same. And we also proved that if a graph is minimally imperfect, then there is a gap. So for minimal imperfect graphs, this polynomial is not SOS. And therefore, odd holes are, it's easy to check that odd holes and odd anti-holes are minimal imperfect graphs. So they are not perfect, but their induced subgraphs are perfect. Proper induced subgraphs are perfect. And therefore, if you write this polynomial for an odd hole or an odd anti-hole, you will obtain a non-negative polynomial, which is not SOS. So here you get an infinite family of non-negative but not SOS polynomials. But let me remind you something. In order to write down this polynomial explicitly, remember this polynomial has omega in it. So we need to know the clique number of the graph. Otherwise, we cannot write the polynomial explicitly. So, but in this case, it's easy. For odd holes, we know that the clique number is exactly 2, and the clique number of odd antiholes is exactly m if it has 2m plus 1 vertices. So we can easily write down this polynomial for odd holes and odd antiholes. Okay. Let me show you a little bit more interesting graph family. This is powers of cycles and their complements. But let me first define what I mean by power, because it may mean different things in graph theory. So the kth power of a graph is the graph obtained from G by adding an edge between every pair of vertices within distance at most k. So here's an example. Here we have a graph G, and so we keep the same set of vertices, but we may have more edges because now we will add an edge between every pair of vertices within distance at most 2. So in terms of the polynomial, we will have the same set of variables, but we may have more monomials because now we have more edges. So now let's consider this graph family. This is a cycle on AB plus 1 vertices to the power B minus 1. Here A and B are at least 3. Here are some examples. So these are more general than odd holes and odd antiholes, because in fact, if B is 2, then you recover odd holes, and if A is 2, then you recover odd antiholes, but these are more general. So these graphs, although they are not minimal imperfect, they satisfy those 3 conditions that were needed to prove that there is a gap between the clique number and the Schreiber number. And since there's a gap, if you write this polynomial for these graphs, then you will obtain a non-negative but not SOS polynomial. How about the clique number? Well, very conveniently, the clique number, I mean, it takes a minute to check this, but the clique number of this graph is exactly B, and the clique number of its complement is exactly A. Okay, so we can write down this polynomial explicitly for these graphs as well. The next graph family is polygraphs. So let me define what these graphs are. So for a prime number Q, which is 1 mod 4, such as like 5, 13, 17, etc., the polygraph is denoted by PQ. And the vertices are simply, you can think of them as integers from 0 to Q minus 1. And then the edge set is defined here. It's not important right now, so let me not describe it precisely, but it is there. So this is a well-known class of graphs. And one thing that we know about them is the following fact. Their Schreiber number is exactly the square root of Q. But Q is a prime number. So the Schreiber number is not an integer. But the clique number is an integer. So there is a gap between the clique number and the Schreiber number. And therefore, if you write the polynomial for these polygraphs, then you will obtain a non-negative but not SOS polynomial. How about the clique number? Because we want to write down the polynomial explicitly. Well, unfortunately, in this case, we don't know the clique number of polygraphs in general. But something better is known. We know a bound, an upper bound on the clique number. This is a very recent bound. It's, I think, from 2021. So this is an upper bound on the clique number of a polygraph. And this bound is always strictly less than the square root of Q, which is the Schreiber number. So what we can do here is, instead of considering PGX, we can go to the more general polynomial, PGKX. If you remember, this polynomial is non-negative if and only if K is at least omega, and it is SOS if and only if K is at least the Schreiber number. So what we can do is we can pick G to be the polygraph, and then K to be between these 2 numbers, which will be between the clique number and the Schreiber number. And therefore, for any K, for any polygraph, and for any K between these 2 numbers will be a non-negative, will give a non-negative but not SOS polynomial. Okay. All right, so these are 3 graph families. As I said, there are many more. You can check out the paper. There are several other graph families. But now I want to describe 3 operations that preserve being not SOS. The first one is a very simple one, adding vertices without increasing the clique number. So here, you start from a graph for which you know that the polynomial is not SOS, such as 5 cycle. Then you can add as many vertices as you want with arbitrary adjacencies, with the only condition that you don't change the clique number. So the clique number of h and g are the same, it's just 2. And then the claim is that the polynomial that you will write for this graph will still be not SOS. I mean, it's always non-negative, and it still be not SOS. So why is that? Because if it was SOS, then the claim is that PHX would be SOS. And why is that? Because of the following remark. So essentially, deleting vertices from a graph corresponds to setting those variables to 0 in the polynomial. But this is true if and only if the clique number doesn't change. And now, if PGX is SOS, you can delete these vertices to obtain h, which means that you can put those variables to 0 in the polynomial. But this is just then a restriction of an SOS polynomial, which should be SOS, but it's not SOS. So PGX cannot be SOS. Okay, so this gives us a way of generating many more non-negative but not SOS polynomials. A little bit more interesting one is graph join. This is a very simple operation to describe. You take two graphs, G1 and G2, and you add all the edges between them, all the possible edges between them. And then one thing to observe with this operation is the clique number of the join is the sum of the clique numbers. And it's not that immediate to see, but it is known that the same thing happens for the Schreiber number. So then what we can do is the following. We can start with two graphs, G1 and G2, for such that for at least one of them, we know that PGX is not SOS, the polynomial is not SOS, let's say for G1. Then do the join, and then the claim is that the join again will not be SOS. So because it's easy to see it, if there is a gap between the clique number and the Schreiber number for G1, so if this is strictly less than this, well, this is always less than or equal to this, then if you go to the join, you will see that this is strictly less than this. So there will be a gap, and so you can obtain many more non-negative but not SOS polynomials using this operation. Okay, and one last operation is this well-known graph strong product. So the strong product of two graphs, G1 and G2, so the vertex set is defined as the Cartesian product of the vertex sets of G1 and G2. And the edge set is defined here. If you know it, you know it. If you don't know it, it's not important right now. So again, let me not describe it, but it is there. But what is important is the following fact. The product, the clique number of the product is the product of the clique numbers. And the same thing happens for the Schreiber number. So again, we can start with two graphs, G1 and G2, such that for at least one of them, it's not SOS. So this is strictly less than that. This is less than or equal to that. And therefore, when you go to the product, this will be strictly less than that. And therefore, you will obtain again a non-negative but not SOS polynomial. Okay. So this, like using results from graph theory, we can actually generate several interesting non-negative but not SOS polynomials. So the next natural question is, what happens on random graphs? If I generate a random graph, G and P, we know that it is non-negative, but is it going to be SOS or not when we write this polynomial? So informally speaking, so here I have the informal version of the theorem. We show that as the number of variables go to infinity, as n grows, when you generate a random graph with very high probability, the polynomial that corresponds to that random graph will not be SOS. So we know that all of these polynomials are non-negative, and we show that with very high probability, they won't be SOS as n grows. So you can think of this in some sense. You can consider this as a discrete confirmation of Blackram's theorem that I mentioned at the beginning. So Blackram's theorem says that if you fix the degree and let n go to infinity, there are many more non-negative polynomials than SOS polynomials. And something similar happens here. You fix the h probability p and you let n go to infinity, then we show that this kind of polynomials, they will be non-negative but not SOS. So with high probability. So there are many more non-negative but not SOS polynomials. And when you look at the formal theorem that we have in the paper, you might realize that sometimes we might require this n to be large, like millions of vertices, in order to obtain random graphs with P, G, and Px not SOS. However, that's not what we observe computationally. We observe computationally that this occurs even for very small values of n. So here we have generated for different values of n and p, we have generated 100 different random graphs for each pair, n and p, and we have counted for how many of them they are not SOS. So as you see here, even for n equals 75, 98 of them, and 98 of 100 graphs, they are not SOS. They are non-negative but not SOS. Okay, and of course, in order to show that they are not SOS, we need to find the clique number, right? But that's not what we did. So these numbers are actually lower bounds, because what we did was we fixed n and p. We calculated the Schreiber number, which is a semi-definite program, and whenever it's not an integer, we just said, okay, it's not SOS. So there may be more actually, but that's the one. And you see here, even for n equals 100, almost all of them, they are not SOS. And one quick note for the SOS community maybe. So note that this provides a very easy way of generating random non-negative polynomials that are not SOS. So fix n and p, right? Generate a random graph, G and p. Look at the Schreiber number, which is a single semi-definite program. If it's not an integer, then you have your non-negative but not SOS polynomial. And what we observe here is that most of the time, it's not going to be an integer. Okay, good. So one maybe last technical thing that I want to mention is the subsets of SOS polynomials. So let me remind you this Cn and Kn formulations of the clique number and the Schreiber number. So in his PhD thesis, Parillo observes that this set Kn is actually the same set as the set of matrices that can be written as the sum of a positive semi-definite and a non-negative matrix. So then I asked the following question. So what happens if we consider some subsets of Kn? So Cn leads to the clique number, Kn leads to the Schreiber number. What would happen if we consider some subsets of Kn? What do we get? Do we get something meaningful in graph theory? For instance, there are these subsets of the PST, the set of PST matrices. These are called diagonally dominant and scaled diagonally dominant matrices. And as a side note, these sets of matrices were studied to obtain some subsets of SOS polynomials that are called DSOS and SDSOS polynomials. So these are simply some SOS polynomials of a particular structure, but that's not what I'm interested in right now. So now my question is, if we write the same optimization problems with this PST replaced by SDD or DD, what do we get? It is surprising, at least surprising to me, that they actually correspond to some parameters that are meaningful in graph theory. So we show that, I mean, I'm not going to give the proof, but we show that this first one, when we replace PST with SDD, is exactly the largest eigenvalue of the adjacency matrix plus 1. And the second one is exactly the maximum degree plus 1. So Cn leads to the clique number, Kn leads to the Schreiber number, and these two numbers, these two sets, they lead to these two numbers. So we obtain the following inequalities. I mean, these are not new inequalities. They were known in graph theory before. So for instance, this one, the largest eigenvalue less than or equal to the maximum degree, it's a very well-known fact in spectral graph theory. But what we do here is actually gives an alternative proof of this fact, okay? And there are several other aspects of this polynomial PGX that I'm not mentioning here in the interest of time, such as finding a separating hyperplane whenever PGX is not SOS, or convexity analysis of this polynomial PGX, or an algebraic notion of imperfection ratio based on the polynomial PGX. And at the end, I will provide an archive link in case you would like to know more. And I'm also happy to talk about them at the end if we have enough time, okay? But for now, let's step back for a moment and see what we have done. So this work establishes the link between perfect graphs and SOS polynomials. And we have seen that using some results in graph theory, we can systematically construct non-negative polynomials that are not SOS, a task which may be of interest to the algebraic geometry and polynomial optimization communities. Then the question is, can we use some tools? Then the question is, can we also transfer ideas in the other direction and bring some value to graph theory? So more precisely, can we use some tools and techniques from convex algebraic geometry and semi-definite optimization to prove or reprove some results in graph theory? For instance, can we give some alternative proofs, some algebraic proofs for some structural results concerning perfect graphs. So I will now give you 3 quick examples of such theorems. So here's the weak perfect graph theorem. It simply says that if a graph is perfect, then its complement is perfect. So this was proved by Lowas in 1972, and there are several different proofs in the literature right now. But it would be nice to give an algebraic proof. So here is an algebraic reformulation of this theorem. If PHX is SOS for every induced subgraph H of G, this simply says that G is perfect. If G is perfect, then this polynomial, which is known to be non-negative, is SOS. So this is the polynomial written for the complement of G. So this simply reduces to showing that a non-negative polynomial is SOS. And it would be nice to give an algebraic proof of this theorem. Just a quick remark here. It's tempting to think that maybe this statement is the same as saying that if PGX is SOS, then PG complement is SOS. Well, that's not true. This is not true in general. First of all, here is an example. Here's a graph G. If you write the polynomial, you will see that it is SOS because there is no gap between the clique number and the Schreiber number. But if you go to the complement, this is the complement of G, then you realize that there is a gap. And so the PG complement will not be SOS. So we really need to take induced subgraphs into consideration here. We really need to use the fact that PHX is SOS for every induced subgraph. Okay. In order to prove this weak perfect graph theorem, we can prove maybe something stronger. This is known as Lowas's characterization of perfect graphs. It simply says that a graph G is perfect if and only if every induced subgraph satisfies this condition, which says that the independence number times the clique number is at least the number of vertices. So one direction of this result is immediate, as every other result concerning perfect graphs. But the difficult direction can be reformulated as follows. If every induced subgraph H of G satisfies this condition, then PGX is SOS. That's it. Then the non-negative polynomial PGX is SOS. So again, it reduces to checking that a non-negative polynomial is SOS. Also, since this characterization is self-complementary, it gives another proof of the weak perfect graph theorem. So we could try to prove this one. And as before, we need to use the fact that this condition holds for every induced subgraph, since otherwise the statement is not true in general. So if you just say that if G satisfies this condition, then PGX is SOS, that's not true. And here is an example. Clique number 3, independence number 2, the number of vertices is 6. So this condition is satisfied, but PGX is not SOS because there is a gap between the clique number and the Schreiber number. And finally, we can be more ambitious and we can try to give a proof of the strong perfect graph theorem, whose combinatorial proof is very long and difficult. As I mentioned, it's more than 175 pages. Again, one direction is immediate, and the other direction reduces to the following beautiful reformulation. It says that if G contains no odd holes and no odd antiholes, then PGX is SOS. So that's it. It again reduces to showing that a non-negative polynomial is SOS. And if you like to work with matrices rather than polynomials, then here's the matrix version. If G contains no odd holes and no odd antiholes, then this matrix here that is known to be copositive can be written as the sum of a positive semi-definite and a non-negative matrix. Okay? These are the same thing. And I really hope that these reformulations could actually lead to an algebraic proof of this strong perfect graph theorem in the future, hopefully a simpler and a shorter proof. But I mean, Annie would know much better, but the reason why I'm hopeful is that there are certain techniques to show that some non-negative polynomials are SOS. So the question here is, can we use those tools from semi-definite optimization to prove such an important structural result in graph theory? Okay, and so this completes my talk, and so let me stop here, and thank you very much for listening.
Thank you, Cemil. Are there any questions for Cemil? So maybe just so what you said about Greg's theorem, and so how we have this discrete reason for why there is this gap between non-sum of squares and non-negative polynomials. I was wondering, is there any hope that you could actually fill part of the space between both cones with such polynomials by adding some parameters to them, or I don't know. Does that make sense? Or
yeah, so maybe can you try to rephrase, because I'm not sure if I understood correctly the question. So what do you mean by closing the gap? That's
or so you know, Greg's result is okay. They're significantly more. So if you're comparing the volume of both cones,
yes,
you know, they're not the same. So
yeah,
are you able to fill that volume between them? That gap in the volume. Which, because it's discrete, I'm guessing no, right?
yeah, yeah.
But I'm wondering if, you know, you could.
I see. Probably no, right? I don't know. And also, like I say here, this is a discrete confirmation of Bleckermann's theorem, but it's for a very specific type of polynomial, right? This PG and PX, which is like degree 4 and like certain. It has a certain structure. But I guess in Bleckermann's theorem, it's like for any kind of polynomial. And as you said, yeah, I think the answer should be no to your question. Although I'm not sure if I fully understood, but I think, as far as I understand, I think it should be no.
Yeah, I'm just wondering if you can modify your PGXs to be more general.
Okay.
Than they are right now.
I see. I think I understand now. Yeah. Then I don't know. then I don't know. Yeah. But that's a good question. I think I understand it now. Yeah. Don't know.
More questions?
So you mentioned that the Schreiber number and the clique number had these really similar formulations. Is there something similar for the chromatic number that's on the other side? Is there, like... Oh,
yeah, this is a good question. So you're asking what set would correspond to the chromatic number? Is that the question? Yeah. So so this lambda max A plus 1, which correspond to this SDD plus NN, it's already an upper bound on the chromatic number, right? So the chromatic number should be somewhere here. So that set that you're trying to imagine should be between STD n plus NN and Kn. But I don't know exactly which set that would correspond to, but this is a good question, yeah. Does it make sense, or did I understand the question correctly? Okay, great.
Does that kind of explain why the lemma 2 that you mentioned, the proof was very between like the clique number and the other number, but then like I was wondering about the relations between how that closes the gap between the chromatic number and number.
So I hear someone is speaking, but I didn't hear the words. Sorry.
Yeah, sorry. Yeah, so I was wondering if Alejandro's question and your answer kind of relates to in lemma 2. You're talking about how the gap equaling the, make sure I get it right, clique number and the, what's that other number called? Schreiber number.
Yeah.
Yeah, and then there's a proof, but then I was wondering how that shows the gap between the Schreiber number and the chromatic number, but I was wondering if that answer has to do with any relationship.
Yeah, I see, yes. So in this lemma 2, we are more on this side, right? We close the gap, as you say, between the clique number and the Schreiber number. But I can confirm that it is also true that a graph G is perfect if and only if the Schreiber number and the chromatic number are the same for every induced subgraph. Yes, but in terms of the set descriptions, like this STD and PSD, and I don't know which set that the chromatic number would correspond to. So like we are trying to solve a very specific optimization problem, minimize K such that that matrix minus KA plus K minus 1J is in some set. And we hope that the optimal value will be the chromatic number, but I don't know what that set is. If I understood the question correctly again, yeah.
Yeah, thank you.
First, so this one.
I guess I'm kind of wondering a little bit about. It just feels as though everything fits so beautifully together.
Yeah.
And you know, but I would never have thought of doing any of that. Using the Muskin-Charles theorem in that way.
Yeah.
So can you give
So-
any?
Are you asking why? That's like how? Well, I have a good answer to this question, but you should promise we will keep this between us. So I have two advisors at Princeton, right? One is Amir Ali, and the other is Maria Chudnovsky. So Amir Ali is working on some of Square's polynomials, and Maria is working on perfect graphs, and so they are both obsessed. I mean, not in a bad way, in a good way. They are both obsessed with their work. So, like as their PhD student in the middle, I had to find something that connects these two. Otherwise, I realized I maybe wouldn't be able to graduate. So that was the main motivation. No, I'm kidding. But yeah, I think it's yeah. I also find it beautiful, to be honest. And yeah, I don't know how to answer this question. Sorry.
Well, let's thank Cemil again for a wonderful talk.
Thank you. Thank you very much.
Yeah, and happy Thanksgiving to everybody. Yeah, it's just so beautiful. It just fits so wonderfully together.
Thank you.
Yeah, I really enjoyed it. Thank you.
Great. So I'll be leaving the meeting then.
Yeah, I mean, having two advisors can be sometimes dangerous, sometimes it can be wonderful.
Yeah, exactly. Yes, thank you very much. Oh, thank you for coming. Bye.
Thanks for coming, Cemil. Bye, everybody.